Now we will try to use lasso for selecting variables in a naive way. So the instructions say, fill in the blanks in the code below. We will use lasso and cross-validation to select variables that predict y. So first thing we're asked to do is to store all the variables except target y in a matrix form. So remember GLMnet required that all the variables that you supply would be in very basic forms, basically a matrix or a vector. So going to transform the data set. So first of all, we deselect column y, right? And then we do say as matrix, and it should be a numeric matrix in the end. If you made a mistake and there were some character vectors or factors within the data set, your matrix will be a character matrix. So let me just comment out this and see what xmat would be. As you can see, it's our values within our matrix are not in quotation marks, meaning this is indeed a numeric matrix that we received. Next we cross-validate lasso regression to pick the correct lambda. So we use this function cv-glmnet. We covered this function in the very first tutorial. Then we say our matrix of variables is xmat, y is data set column y, and alpha is, we want lasso, so we put 1. If we wanted to reach, it would be 0. So we do this, and then we want to plot the results of cross-validation, remember, and we would say plot CV lasso. And voila! Again, here we see that we can have very high lambda, which is basically when lambda is very high, it's an intercept, and as you can see here, it just selects one variable. And these are more flexible models, close to OLS. So as you can see here, lasso, it selects more than 25 variables to predict y, but still less than 100. So now we are going to look at which variables the lasso did actually choose. So remember, this is just the results of cross-validation. CV lasso object has many different lasso at different levels of lambda. Now we want to extract exactly the model that corresponds to the one that minimizes the cross-validation errors. So we want this exact model back. To do so, we store best lambda from the CV lasso object. So this CV lasso object will store the value of the best lambda as CV lasso and lambda mean. Let's see what best lambda is. A 0.24. Okay, now we will run actually the lasso. We will store the lasso by running glmnet on, again, x matrix. Y is our data set y. Alpha is equal to 1. And the lambda, what lambda should we use? We should use best lambda that we just did. But then we want to get the coefficients of the lasso regression that were not put to 0 by at best lambda. So we do coefficient lasso regression. Let's see what kind of class it is. What does coef function return back from the object called lasso reg? And it says it's a matrix, but it's also a sparse matrix. So we want to actually say no, it's actually store it as matrix. We store it as matrix, and as you can see, these are the variables that we supplied to lasso, and many of them are 0. So lasso did not choose, for example, variable 24, 25. Next, we convert this into a data frame. Why couldn't we do it earlier? Now apparently when it's sparse matrix we cannot directly convert it to data frame. It's just we need the transition through a matrix. Now it's a data frame, as you can see, with one column as 0. So this, as you can see, is not a column in itself, it's a name of the rows. But we want this to be a proper column. So we mutate, we say coefficient names is the row names of the matrix that we are piping back. This dot is again a placeholder and says take the object that we are piping into here and take its row names. And its row names will be this. So what happens now is that you have now coefficient names, a character vector. Now we rename as 0 this column into something more meaningful like estimate. So this is an estimate, right? See, as you see, we renamed it, and the next thing that we do, we filter out everything that is equal to 0. So we want to keep all those coefficient names that have that Lasso calculated to be an important predictor. Their estimates strictly greater than 0. So we say filter by keeping only those whose est column is different from 0. And here you can see we are left only with 28 rows. That's it, and we store this. So how many variables did Lasso choose excluding the intercept? It is 27, because we have 28 rows including intercept. Mostly you also see it kept D as one of the predictors. In fact, it's not given that D will remain as an important predictor. Finally, we look at no less with y as a dependent variable and d, our treatment variable of interest, plus all other variables that have been selected by Lasso. So we say dataset select y, d, and how do you keep all the selected variables? You say coef names of Lasso coefficients. Let's see what it gives us. An error. Sorry, I should have removed the intercept, right? Because there is no variable called intercept. That is why this will select only y, d, and all other variables that were selected by Lasso. Notice that coefficient, so here this one will already include d, but it will not duplicate. If you pass d, for example, again here, d, 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 it will not select d multiple times. It will not create new variables. It just select unique values that of things that you ask. Next stop is to run the regression. Linear model, y on everything, with using the data that it has been piped so far to here. This runs the regression and we want to see the results. We will use tidy. That's it. As you can see, it ran the regression and it found that d coefficient in front of d is equal to 10. Whereas, which is completely incorrect because the true effect is 1. And it rules out that the effect is 1 because standard errors are very small. Finally, I show you what is the correct true causal effect. And as you can see, there are 3 variables, v1, v2, and v3, that are confounders in this situation. So if we run an OLS, lm, y on, so there are several ways. I will do like this. Data set, select y, d, v1, v2, and v3. And then I want to run a linear model of y on everything else that we have selected, and the data is the data that we supplied through the pipe. And I want tidy at the end. So what do we get here? Oh my god, it's 15. It's super large. It's actually even more wrong as a point estimate than the previous one. But what do we see here? Standard errors are huge. And it means that actually it doesn't rule out that d is equal to 0 or d is equal to 1. At least we are not lied about how certain we are that it is actually 15. So this is what we actually want.